In this problem, we're given a particular network of capacitors and asked to find the charge on one of them. So on the left here, there's an EMF voltage source at 10 volts. Then we got a series of 4 capacitors. We need to find out the charge on the 6 microfarad capacitor. When we're confronted by a network of capacitors like this, and we need to figure out the charges on them, usually what we need to figure out is the total charge on the system. We do that by combining capacitors in series and parallel, so we can figure out a total effective capacitance. And once we have that, we can figure out the charge on that effective capacitance and work backwards in order to figure out the charges and the voltages on the individual components. So if I want to combine these things in series and parallel, I need to identify series and parallel components, and I can actually see that 2 of these capacitors here are in parallel. And I can tell they're in parallel because the tops are connected and the bottoms are connected. That means the voltage has to be the same across both capacitors, and if the voltage is the same across both capacitors, they're in parallel. Now the law for combining parallel capacitors is just that the total capacitance is C1 plus C2. So I can redraw the circuit, my EMF source. I can draw C above and C below. This is 3, this is 4, everything's in microfarads. Now, when I combine the 2 parallel capacitors, this is going to result in a net capacitance of 16 microfarads when I combine them in parallel. Now I've done this, I can look at the circuit and I see that I actually have all 3 capacitors in series. If I start here on the upper left-hand corner and go around the circuit, I have to go through the 3, then the 16, then the 4. If these are all wired together, so I have to go through one, then the other, then the other, this means that these things are in series. I can combine them in series. So the law for combining 3 capacitors in series is 1 over C1 plus 1 over C2 plus 1 over C3 is equal to the total net capacitance. Okay, given this that this is true, I can combine these things to find a total capacitance. It's equal to 1 over 3 microfarads plus 1 over 16 microfarads plus 1 over 4 microfarads. Okay, and I can just combine these things and add them up. When I do that, I can find the total capacitance in the system when these things are in series, and I get 1.55 microfarads. Okay, so this circuit acts like a 10-volt EMS source connected to a 1.55 microfarad capacitor. Now that I know this, I can calculate the total charge that's stored in the system on these capacitors. Q is equal to CV. That implies that the Q that's stored is going to be equal to the capacitance, 1.55 times 10 to the minus 6. We write farads as coulombs per volt times 10 volts, or 15.5 microcoulombs. Okay. Now remember, we got this total effective capacitance by combining 3 capacitors in series, as you can see up here to the left. And we calculated the charge stored in the system. Parallel capacitors have the same voltage. Series capacitors have the same charge. So if I look back up at my diagram here on the left, the 3 microfarad, 4 microfarad, and 16 microfarad effective capacitor all have the same charge on them because they're in series. So now I've calculated the charge of the system, I actually know the charge on all of them. In particular, I can look at the 16 microfarad capacitor, which is actually 2, remember, it's 2 combined in parallel. And I know that the charge on this capacitor is equal to 15.5 microfarads because we calculated the total charge on the system and we know the charge is the same on all the series capacitors. That means I can actually calculate the voltage across this particular capacitor. That's Q over C, or 15.5 microcoulombs divided by 16 times 10 to the minus 6 coulombs per volt. Okay, so I can actually figure out now what the voltage across that capacitor is. Doing a little bit of math, I find that it's 0.969 volts. Okay, so this is the voltage that's across that 16 microfarad capacitor. But remember, that was really 2 capacitors. The 6 microfarad capacitor we won, a 10 microfarad capacitor. Okay, and I now know the voltage difference across these 2 capacitors, 0.969 volts. It's the same because they're in parallel. Well, if I know that the voltage across the 6 microfarad capacitor is 0.969 volts, I can calculate the charge on that capacitor. Q is equal to CV, or 6 times 10 to the minus 6 microfarads, so coulombs per volt, times 0.969 volts. Do a little bit of multiplication. I can find that the charge stored on this is 5.82 microcoulombs. And that's the answer.